Electric vehicles are really becoming, the future of how we get around. Super clean, quiet, and just remarkably efficient. I mean, think about this. The US Department of Energy says regular gasoline cars, they only use maybe 14 to 30% of their fuel energy to actually move the wheels. EVs, though, totally different story. We're talking 74 to 94% of battery energy going straight into motion. That's a huge jump in efficiency. But let's be real, EV batteries still have their challenges, right? Shorter ranges than a tank of gas, often. And those recharge times, sometimes hours, not minutes. Now, what if I told you there's this like subtle, almost hidden energy drain happening inside EVs? An inefficiency that, if we could fix it, could actually stretch the range even further. So today, we're doing a deep dive into some really fascinating research. It tackles exactly this, the power management systems in electric vehicles.
Right. And our mission here is to really unpack the uh, the unique approach, the innovative ideas, and maybe most importantly, the significant academic contributions this specific research offers. We want to make EVs even more energy efficient. We'll be looking at why this solution, this particular one, really stands out. What's its novelty? What's its specialty in the field?
Okay, and the paper we're digging into today, it's titled Event Prediction Algorithm Using Neural Networks for the Power Management System of Electric Vehicles, and it was published in the Applied Soft Computing Journal. So, this hidden energy drain,
Right.
where's it actually coming from? Let's start with the basics. What is a power management system in an EV?
Okay, think of it as the car's energy brain. Its main job is to decide which electronic control units, or ECUs, need to be on or off at any given moment.
ECUs, those are like the mini computers running everything from cruise control to parking sensors, yeah.
Exactly. And the power management system tries to save energy by switching off the ones that aren't needed right then. Simple enough, right? Well, here's where it gets really interesting, because the problem is actually a bit counterintuitive.
Right.
Imagine the car changes state, say, from cruising smoothly to driving slowly in city traffic. At that exact moment of transition, the energy needed, the overhead to switch those ECUs on or off, can sometimes be more than the energy you save by switching them off briefly.
Whoa, okay, so switching things off can waste energy.
In certain situations, yes. The researchers call these energy inefficient state transitions.
Huh. It's like flicking a light switch off to save power, but the switch mechanism itself uses more energy than just leaving the light on for that tiny moment you plan to have it off.
That's a great analogy.
Yeah.
And picture that happening over and over again during a drive. These little inefficient switches, they add up. They start to chip away at the EV's overall efficiency.
Okay, that makes sense. So how do they figure out when it's inefficient?
This is where a concept called break-even time, or TEED, comes in. It's basically the minimum amount of time an ECU needs to be off for the energy saving to actually outweigh the energy cost of switching it off and on again.
So TB is like the tipping point.
Precisely. If an ECU gets switched back on before it hits that break-even time, the whole transition was actually a net energy loss. The paper gives a formula, but the core idea is time off needs to be longer than TB.
Right. So an unacceptable state transition, that's the term they use, is when the system predicts the ECU will be off for less time than this break-even point.
Exactly. Those are the transitions you want to avoid because they just waste energy.
And the problem is current systems can't see this coming.
Correct. Today's power management systems, the ones actually in cars, they react based on the current state. They don't predict the future duration or calculate that TEEB. They just can't detect these unacceptable transitions ahead of time.
Which leads to the big question. How do you predict something like that in real time inside a moving car?
That's the challenge they tackled. The proposed solution has two key parts. First, identifying these unacceptable state transitions, using that break-even time concept. If the algorithm predicts an unacceptable transition is about to happen, it just tells the system, nope, don't switch. Stay in the current state. Avoid the overhead entirely.
Okay, so prevention. What's the second part?
The second part is really clever. It's called adaptive training speed for the neural networks they use.
Ah, neural networks. So they're using AI to predict these transitions.
Yes, the algorithm learns from past driving data, vehicle speed, but also more complex things like weighted moving averages, stochastic D%, relative strength index, basically patterns in the sensor data. It uses this history to forecast whether the next potential state transition is going to save energy or waste it,
Yep.
based on that break-even time idea.
But you mentioned speed. Predicting is one thing, but doing it fast enough in a car must be tough.
Extremely tough. This is where the constraints get really tight. The car's main system makes decisions about operating states every half second, 0.5 seconds.
Yep.
So the prediction algorithm, it has to do all its learning, its training, and make its prediction in just 1/10 of a second, 0.1 seconds.
Wow. 0.1 seconds. That's incredibly fast. How do they even manage that?
That's where the adaptive training speed comes in. It's algorithm 1 in their paper, and it's designed specifically for this. It actually speeds up or slows down the neural network's training based on how well it's been doing recently. It looks at the history of training errors. If errors are dropping nicely, it might speed up learning. If errors are bouncing around, it might slow down to stabilize. It constantly adjusts.
So it learns how to learn faster, basically.
In a way, yes. It helps the training converge quicker and more reliably, allowing it to hit that super tight 0.1 second deadline. It's not just about being smart, it's about being smart fast.
Okay, this sounds genuinely innovative. Let's talk about the academic contributions here. What makes this research, special or novel compared to other work? The paper highlights four specific things, right?
Absolutely. And these really define its contribution. First, they propose a novel energy model for the whole electronic control system in the car. What's new is that it estimates both the potential energy savings and the energy overheads when ECUs change modes. It digs into the details, ECU operations, parameters, network delays, giving a much more complete picture for balancing energy.
Right, not just looking at the savings, but the cost too. A holistic view. Okay, what's second?
Second, they developed a tailored supervised learning algorithm. It uses neural networks, but it's specifically built to predict if a state transition will be energy profitable. The novelty here is that it learns based specifically on the break-even time and predefined conditions related to that. It's not a generic predictor. It's tuned precisely for this automotive energy-saving problem.
Makes sense. Tailored to the task. And the third point, you mentioned the speed.
Yes. The third is that groundbreaking adaptive training algorithm. This is huge, both academically and practically. It adjusts the neural network's parameters based on its own training history specifically to meet that strict 0.1 second time limit. This directly tackles a major barrier for putting complex AI like neural networks into real-time systems like cars. It makes the theoretical practical.
The difference between a cool idea and something that could actually work in my car.
Got it.
And the fourth contribution.
Fourth, they backed it all up with a rigorous feasibility study. They didn't just propose it, they tested it thoroughly. They looked at execution time, how accurate the predictions were, the average training error, all under simulated real-world vehicle conditions. This empirical proof adds a lot of weight and confirms it's actually applicable.
Okay, so they built the model, developed the algorithms, made it fast, and then proved it works in simulation. What were the actual results? What kind of energy savings did they see?
They ran simulations using real driving data for diverse data sets from Europe, New York City, standard EPA driving cycles, even Australia,
Yeah.
capturing different driving styles.
And the outcome?
The headline result is pretty compelling. Their algorithm, especially using that adaptive training speed with artificial neural networks, ANNs, managed to improve the energy dissipation of the electronic control system by 5% to 7%.
5 to 7% just from managing ECU switching better. That actually sounds quite significant for what seems like a background process.
It is significant in the context of optimizing every last bit of energy in an EV. Every percentage point counts towards range.
You mentioned they compared their adaptive training to other methods. Did anything else come close? Was there a trade-off for that speed?
That's a really important point they investigated. They tested against 6 other standard neural network training algorithms, things like gradient descent, adaptive moment, RMS prop. Now, interestingly, sometimes gradient descent had a slightly higher raw accuracy in predicting the unacceptable transitions, but
There's always a but.
the crucial test was execution time. When they measured how long each algorithm took to make a prediction, only their adaptive training speed and one other, adaptive moment, consistently finished within the required 0.1 seconds.
Ah, so the others, even if sometimes slightly more accurate on paper, were too slow.
Exactly. Gradient descent, for instance, took much longer. Its predictions would have been outdated, expired, before the system could even use them. They'd be useless in a real car scenario.
So it's not just about being right, it's about being right on time. That really hammers home the practical value.
Precisely. And they also checked for negative side effects like, did the algorithm wrongly block good energy-saving transitions? They found these instances were minimal, so it delivered the benefits without significant drawbacks.
That's the key then, isn't it? For you, the listener, it highlights that the smartest algorithm isn't always the best if it can't operate within the real-world constraints, like the split-second timing needed in a vehicle. This adaptive approach finds that sweet spot between accuracy and speed.
leading to real, measurable energy savings.
So this whole deep dive, it really pulls back the curtain on how these seemingly small things, like ECUs switching on and off, can add up to a noticeable energy drain in complex systems like EVs. And it powerfully shows how targeted AI, specifically these neural networks, combined with smart adaptive training methods, can find and fix these hidden inefficiencies.
And the researchers are planning next steps too. They want to use even larger data sets and test this on actual prototype vehicles to see how well the model translates from simulation to the real metal.
So something for you, the listener, to think about.
Right.
As EVs become more and more common, how might these kinds of really nuanced AI-driven optimizations working silently behind the scenes change what we expect from vehicle range and efficiency? And maybe even broader than that, what other hidden energy drains and all sorts of technology around us could AI potentially uncover and help us solve next? Lots to consider. Thank you for joining us on this deep dive.